Welcome back, everybody. We're still going to be talking about transformations of quadratics today. So again, we're taking this quadratic parent function and we're going to change it in some way. Last time we did translations, which was moving the graph from side to side or up and down, as well as reflections, which is flipping it over one of the two axes, either creating a sad parabola, or the same exact looking parabola if we reflected it over the y. But today we're going to be doing dilations. Now again, you probably have heard of dilations before. It's going to be taking something, either making it bigger or smaller. But since we're dealing with quadratics, it's not like a triangle is going to become like a bigger triangle, like a dilation you might have seen before. We're going to be stretching and shrinking, making wider or narrower these parabolas. So we're changing the shape a little bit, making it narrower or wider. But before we get into that, I have a couple questions for you. These are things that we're going to need to know about for today because I'm going to be referencing them a lot. There are two types of numbers in the world, okay? The two types of numbers are as follows. You have Dolly Parton numbers, which I'm going to call Dolly numbers, and you have Jennifer Lopez numbers, so I'm going to call those J-Lo numbers. Okay, if you don't know who these two awesome singers are, I'm going to add a picture of both of them. Here's J-Lo. We all know who she is. Hey, J-Lo. Okay, she just did the Super Bowl. She's awesome. That's J-Lo. And then we also have Dolly Parton. Let me grab the picture of her. This is Dolly Parton. Some people say, that's Miley Cyrus's aunt. Yeah, it's her godmother in real life, but her aunt from Hannah Montana. Yeah, so there are two types of numbers in the world. Some of them we call Dolly Parton numbers, and some of them we call J-Lo numbers. It has to do with the way these two ladies look. Now, listen here. This is the way I learned it and the way it stuck in my head. So there's two major differences between these two women. Let me show you the two major differences between the two types of numbers. This is a Dolly Parton number, and this is a J-Lo number. Why do you think I'm calling them that? Yeah, there are some differences in the way that they look, and there are differences in these fractions. Fractions that are bigger on top are considered Dolly Parton numbers. So things like whole numbers, 5, which is like 5 over 1, or 10 over 3, or 4 over 3, all of those are Dolly Parton numbers. Okay, so all of our regular whole numbers, those are all Dolly Parton numbers. J-Lo numbers are what I sometimes call true fractions of like 3/7, 1/2, 1/10, which can be written as 1/10. These are fractions that are bigger on bottom. So we're going to be calling those J-Lo numbers. Now I'm going to reference these types of numbers all day today, so make sure you know what I'm talking about, and we'll be good to go. Now, these transformations that we call dilations are created by multiplying either a Dolly Parton number or a J-Lo number to the front or inside of these functions. So when we're dealing with what are called vertical dilations, so stretches that happen vertically or shrinks that happen vertically, we're going to be multiplying a number in the front. So you might want to bring attention to the fact that this number is going to be multiplied in front of the parent function, in front of f of x. Now, if that number is bigger than 1, if a is bigger than 1, that means that we're dealing with a Dolly Parton number. Because it's bigger than 1, it'll be bigger on top. That is going to create a narrow graph for us. So it looks narrower than the parent function. That's called a vertical stretch. But if the number we multiply in front, so it's the same place, if that number is a J-Lo number, meaning it's between 0 and 1, is a true fraction, I'm using air quotes but you can't see me, this is going to create a wider graph. So the shape has become wider than the parent function. Okay, so there's two new vocabulary words for you. Vertical stretch, that's narrower. Vertical shrink, that's wider. You might also see the word vertical compression. Compress and shrink. But when we deal with our horizontal dilations, we're going to be multiplying those numbers inside. And now I know we're going to be multiplying these numbers inside because we have that acronym that we learned about last time, HIO. It stands for horizontal transformations occur inside the function and go the opposite direction from the verticals. So that means a horizontal stretch is not going to make this graph narrower. It's going to be the opposite. It's going to make the graph wider. Now the numbers that create this are always going to be JLO numbers. When we have a JLO number, it is always a wider graph. It just depends if it's horizontal or vertical as to whether it's a stretch or a shrink. But JLOs will always make it wider. In a horizontal shrink, the number that we're multiplying inside that function, see how it's inside the parentheses? If it's a Dolly Parton number, so it's bigger than 1, it's still going to make that graph narrower, but it is now called a horizontal shrink. Now, I fully understand that we are learning two concepts that seem like they're the opposite, so to keep them straight is a little bit difficult. I fully agree with you. Here's some things to remember. Multiplying in front is vertical. Multiplying inside is horizontal. Horizontal is inside and the opposite. Dolly Parton numbers always make the graph narrower. And JLO numbers always make the graph wider. Let's just look at a few examples on the inside of these notes, kind of like we did in the first transformations lesson. Okay, we're going to look at each individual transformation. Now this is a vertical stretch. The reason I know it is a vertical stretch is because I'm multiplying a number in front of the parent function, in front of the parentheses. And that number is a Dolly number. 2 is a Dolly Parton number because 2 can be written as 2 over 1. It means 2 is bigger on top. Now we know Dolly Parton numbers always make my graphs narrower, and here's why. What we're saying to take the output, the coordinates here, and instead of plotting them just like the parent function, we're going to multiply these numbers by 2. So 1 times 2 is 2, and 4 times 2 is 8. Again, 1 times 2 is 2, and 4 times 2 is 8. So when I plot all of these coordinate points together, I have a narrower graph because I've multiplied that Dolly Parton number by 2 and squeezed it in. That's a vertical stretch of the parent function. But if we multiply a number in front that is not a Dolly Parton number, but is instead a JLO number, bigger on bottom, we're going to be looking at what's called a vertical shrink or compression. But I'm going to use the phrase vertical shrink. You just might also see compression places. Now this number again is a JLO number. JLO numbers make my graphs wider. Here's why. Instead of multiplying by 2 like I just did for the vertical stretch, in a vertical shrink, I'm multiplying by a true fraction, which means I'm halving the distance between the y-intercept and the x-axis, and the coordinate. So that means we're getting wider for every single one of these. Half the distance, half the distance, half the distance. So when I play connect the dots here, this graph is actually wider than the one we started with, than with the parent function, because we used a JLO number, a true fraction, between 0 and 1. Vertical stretches and shrinks makes a lot of sense. You have your Dolly Parton numbers, you have your JLO numbers. I will tell you that when we get to the horizontal stretches and shrinks, even I slip up in what I'm saying every once in a while because it's just opposite of what we want. Anytime you have a horizontal transformation, you got to think, all right, this should show up inside the parentheses and go the opposite way than I think it will. Okay? What kind of number do we have inside these parentheses here? Yeah, that's a JLO number. If we remember, JLo graphs should always get wider. And even though this says stretch and we're getting wider, that comes from the number that I'm multiplying. Basically, what happens here is since that 1/2 is inside, it's going to get squared, which really means I have 1/4, because 1 squared is 1 and 2 squared is 4. So instead of taking half of the output, I'm taking 1/4 of the output. It's going to be like so small, something like this. And look at automatically how wide this parabola is from that JLo number. Because it was inside, it gets extremely small really fast. But that is considered a horizontal stretch, the opposite of what we think since it's getting wider. For a horizontal shrink or compression, what kind of number is inside the parentheses? Is that a Dolly Parton number or a JLo number? Yeah, that's a Dolly number, because any whole number, remember, it can be written as that number over 1, and that's bigger on top. That's a Dolly Parton number. And the reason that this actually gets narrower, because we know Dolly Parton numbers always make their graphs narrower, is because, again, since this 2 is inside, it's going to be distributed to that squared, which means 2 squared, that's 4. I'm actually multiplying each and every coordinate point by 4. It goes off the screen really, really fast. So when I draw this parabola, it's narrower because it was inside. Oop, I missed. That'll do. Sorry, y'all know my parabolas are terrible. Our goal today is to be able to talk about the dilations of these quadratics, how we change their shape, getting them to be narrower or wider. It all has to do with where the number we are multiplying is. Is it in front or inside, vertical or horizontal? And is it a Dolly Parton number or is it a JLo number to get wider or narrower? We'll continue to practice these transformations in class.